Hi, my name is Flavio Francisco Camacho Torres, and I'm going to present my project, Blood Pressure Measurement in the Distal Arteries. And for the content, I got the introduction, then the description of the system, the mathematical model, numerical simulation, and the biological implication. For the introduction, the cardiovascular system is one of the systems which need to be tracked closely to assess the patient's state. This system is characterized by several parameters which serve as important indices of cardiac and vascular functions. There are many models elaborate to study the dynamics of the blood. So we wanna center in the arteria circulation. All these models have different equations, but in this model of the arterial circulations, all these models of the arteria had three elements, which are the same for every model. One is the arterial resistance, that is the resistance of the arteria to the blood flow. Then is the arterial compliance. This is the relationship of pressure and volume of the arteria. And the blood inertance that represents the blood mass, which is accelerate and decelerate of the pumping of the heart. For the description of the systems, we're gonna use the Winskessel model. The Winskessel model is developed by Otto Frank. In this model represents the source that pumps blood into the arterial system. But we're gonna use the modified Winskessel model that use this same system, but we're gonna try to measure the pressure in the distal arteria. That is the arteria more close to the muscles. So here's the model, the circuit, and we got Q, that is the flow. CAP is the compliance of the distal arteries. The CAD, the compliance of large arteries. RA is the resistance of the system. L is the blood inertance. PV is a constant of the flow of the blood. And PAD is what we want to measure, that is the distal pressure. We got the parameters of a normal person, and the parameters of we wanna measure the pressure of a person with hypertension. So we're gonna change the parameters to simulate a person with a problem in the heart. For the mathematical model, we take the circuit, and with the nodes of the circuit, we're gonna obtain the main equations. these equations, we're gonna obtain the currents. We need to apply an integral differential model, and then for this model we're gonna apply the Laplace transform, so we can obtain the transfer function. Then we're gonna substitute some values of the equation, and there is there are the equations, and we got the transfer function. For the numerical simulation, we're gonna use a PID controller, and we got the blocks for the healthy and the person with hypertension. So we're gonna try to use the controller to approximate the hypertension response to the healthy person. We got this model built with the blocks with the equations of the integral differential model we use in the mathematical model, um, and these blocks of the diagram we obtain this response. The first in the first graphic, we can see the healthy person, and with the variation of the parameter, we can see the hypertension person has a lower pressure, arterial pressure. So in the other graphic, we can see the controllers help this hypertension person to adjust the the signal to be equal to the healthy person. For the biological implication, so we analyze the system and the model, and we can see that we can demonstrate the that the pressure can be measured by this type of models. We compare the signals, and we can see that modifying some parameters affects directly to the pressure. And with the PID controller, we modify this signal to help and make the to be a normal signal. For the this for this project, I think we can applicate this model to, for example, a stent, because the stents what makes is to replace the arteria and help to let the flow of the blood mm, pass and make the pressure normal. So with this controller and this model, we can make the to the creators of the stents use the parameters obtained in the controller to adjust the stents and make them mm, repair or help the arteria to function normally. And this is all for me, for my part, and thanks for the attention.